Euclid's Elements, Book 3, Proposition 35. If in a circle two lines cut one another, then the rectangle contained by the segments of the one will equal the rectangle contained by the segments of the other. If we have a circle and we have two lines that cut one another, so A, B, C, D, if they cut one another at the center of the circle, then obviously all these lengths are equal as radii of the same circle. And therefore it's manifest that the rectangle contained by this equal segment and this equal segment will be equal to the rectangle contained by this and this. In fact, they're squares. So the square made by this figure is the same as the square made by this figure. All right, so what about if they don't cut each other at the center of the circle? So they cut somewhere else. How do we prove that? Well, it's a little more work, but we can do it. So let's say they look more like this, where they cut each other not near the center. So we have AC and BD, and they cut each other not at the center of the circle, but rather here at point E. So the first thing we'll do is take the center of the circle, and we'll connect. From F, we'll draw a line perpendicular to AC and perpendicular to BD. And then we can connect FB, FE, and FC. And the first thing we can note, and here's what we're trying to prove. We're trying to prove that the rectangle contained by AEEC, so the segments, so here's what we're proving, that the rectangle contained by AEEC, this rectangle, will be equal to the rectangle contained by these segments, BEED. So the first thing we'll do after we've taken the center, drop a parallel, perpendicular, we're going to realize that according to Book 3, Prop 3, that if from the center of a circle a line be drawn at right angles to a segment, not through the center, then it will bisect that into equal parts. Therefore, this point here, we'll call this G, and we'll call this H. So AG is going to be equal to GC. They'll be bisected. Likewise, BH will be equal to HD. And that means if we look at line AC has been cut into equal and unequal segments. So it's been cut into equal segments at C, or at G rather, and at unequal segments at E. And according to Book 2, Prop 5, when a circle is cut into equal and unequal segments, then the rectangle contained by AE, EC, plus the square on GE will equal the square contained by GC. So let's bring that up here. So since this is true, then we're going to add the square on FG to both sides of this. Here, we'll just do it here. So we're going to add the square on FG to both parts of this equation. So equals added to equals, the remainders are equal. And what we're going to get is the square on AE, or the rectangle contained by AEEC, plus the square on GE, plus the square on FG is equal to the square on GC, plus the square on FG. Now we're going to invoke the Pythagorean theorem, book 1, 47, prop 47. And we're going to notice that the square on GE and the square on FG, those are the legs of this right triangle. And therefore, the sum of these two legs, squares on these two legs is equal to the square on FE. So we're just going to replace this with the square on FE. And likewise, when we look at the square, we look at this rectangle, again, the right triangle FGC, we see that the square on GC plus the square on FG is equal to the square on FC. So this becomes the square on FC. So we can rewrite this as AEEC, the rectangle here, plus the square on FE equals the square on FC. And we can note that FC is a radius and FB is a radius, therefore the squares on them, since those are equal, the squares on them will be equal. So we could replace the square on FC with the square on FB. So let's do that. Let's make that substitution, and we'll say that the square on the rectangle contained AEEC plus the square on FE equals the square on FB. Well, we can do the exact same process with line DB, and won't have to go through it all, but the end result is that the rectangle contained by BE, ED, plus the square on FE will be equal to the square on FB. And this is the same process we'll use 2.5 and prop 47 to get to this. Well, now, if we look at these two expressions, these two things are both equal to the same thing, therefore they're equal to each other. Therefore, we can say AEEC plus the square on FE is equal to the rectangle contained by BEED plus the square on FE. And we can see they both have a common term, the square on FE, so we can remove equal things from both sides and the remainders are equal. So if we remove this and this, then that which remains is simply this, AEEC is equal to BEED. And that's exactly what we were trying to prove. So the rectangle contained by this segments are equal to the rectangle contained by these segments when they cut each other in a circle. That's what we're given to prove, and so we can conclude with QED.